Now we've given you some idea of how electrons are filled in orbitals in an atom, but still things are pretty vague. So now I'm going to develop a system for filling electrons in orbitals, which orbitals are at a lower energy and which ones are at a higher energy, and we're going to figure out everything. So there are certain rules which we're going to follow. The first rule is that electrons, it's the old rule that we discussed previously, electrons will fill the lowest energy orbital first. Now, this means that electrons are going to go into the most stable configuration first. Now, how do you know which one is the lowest energy orbital? That is determined by a simple table which is called it's called the Aufbau principle. It's a simple table which you can construct very easily. That table is that I'm going to show you how that this is 1s, this is an s orbital in the first shell, then there's 2s, then you have 3s, 4s, 5s, and remember the 2 stands for the s orbital in the second shell, the 3 represents the s orbital in the third shell. Then you have another column over here which says which gives you 2p orbital, 3p, the p orbital in the third shell, 4p, and 5p. Then you have the d orbitals, you have 3d orbital, you have the 4d orbital, and then you have the 5d orbital. In the fourth shell, you also have the f orbital, 4f, 5f, and it keeps on going. It continues on and on because you have certain elements are really, really big, but you don't need to worry about really large elements. So the way to fill electrons is if you draw this table, draw diagonals around it, diagonal arrows. So I'm drawing these diagonal arrows. So to figure out how electrons will be filled in an atom, starting from the lowest energy to the highest energy, highest energy. So let's start off by looking at the table. If you start following the arrows from the one that is lowest down, the lowest energy orbital is going to be the 1s orbital. Then you're going to have, you follow the second arrow, and that says the 2s orbital is going to come next. Then you have the 2p orbital. And remember, the 2p is actually composed of three orbitals, which is 2px, 2py, and 2pz. Remember one thing, that the 2p entire 2p orbital, the orbitals are exactly at the same energy level. So these are at the same energy. Then after the 2p you have the 3s orbital. After 3s you again have the 3p orbital, which is 3px, 3py, and 3pz. And again, since they all comprise of the 3p orbital, they are called the 3p orbital, they have the same energy. Then after the 3p orbital you have the 4s. If I continue on below this, you have the 4s orbital, and after 4s you have the 3d orbital, which basically comprises of 5 orbitals: 3d xy, 3d xz, 3d 3d yz, and 3d x square minus y square, and then you have the 3d z square. And remember this, since they're all part of the 3d orbital, they are exactly at the same energy level. So these 5 orbitals are at the same energy. Then if we keep on moving after the 3D, you might have noticed you have the 4p and the 5s orbitals. So you have the 4px, 4py, and the 4pz orbital. Again, these 4p orbitals are exactly at the same energy level. And after 4p, you have the 5s orbital, and so on and so forth. So this keeps on continuing until the table runs out, but you don't need to go very far. You don't need to actually even go till 5s, because elements that are going to come in AS chemistry are going to be limited to 40, 30, 40 electrons, which so you don't need that many orbitals to fill electrons. Now we're going to move on to the third. This is the OVO principle. This basically tells you that the s orbital is going to be filled first, then the 2s, then the 2p orbital, then the 3s, after which the 3p is going to be filled, then 4s, then the 3d, then you're going to have the 4p, and then the 5s orbital, and so on. And how do you get the ordering of these orbitals according to their energy levels? It's determined by the OVO principle, or the simple table that you can construct while you're giving your paper. It's very simple to construct, and hopefully you're going to remember some of the electronic configuration, some of this by heart. If you practice it a lot, it will automatically be very easy for you to remember this. Now, moving on, let's discuss the third point. Now, the third point that we're going to discuss is that within a shell, a specific shell. For example, you have I'm talking about the third shell. In the third shell, I have the 3s orbital, the 3p orbital, and the 3d orbital. Remember one thing: electrons are going to first fill 3s orbital, then they're going to fill the 3p orbital, and then the 3d orbital. So within a specific shell, the s orbital has the lowest energy. And remember, we're talking about within shell. We're not comparing 3s with the 2s or the 2p orbital. We're comparing all the orbitals in the third shell or within a shell. So the lowest energy orbital is always going to be the s orbital within a shell, after which you're going to have the p orbital, which is going to be at a higher energy level. Then you are going to have the d orbital, and then the f orbital. So this s orbital is going to be the lowest energy orbital within a shell. And moving on to the fourth point. Now, this fourth point is very important. We've already discussed that the p orbital is actually comprising of three separate orbitals. For example, let's talk about the 2px, 2py, and 2pz. Now they are basically at the exact same energy level. So they are exactly at the same energy level. So when, and let me draw the 2p orbital. The 2p orbital, since it's in the second shell, it's going to be slightly bigger than the bigger orbital. This is the, let's say this is the y-axis, and this is the 2py orbital. Then you have the x-axis. This over here is the x-axis, and over here, this here represents the z-axis. So you have these three orbitals existing at the exact same energy level. So if electrons are filling the 2p orbital, then they will always fill in a single manner. In a single manner first. What that means is, if an electron occupies the 2px orbital, then another electron comes in, then that is going to occupy the 2py orbital. Why? Because this electron is going to repel it. So if an electron fills the 2px orbital, there's one electron in the 2px, The second electron is going to come into the 2p-y orbital. Why? Because there's electron repulsion, so it's going to go automatically go into the empty orbital instead of filling the already half-filled orbital. So, and if another electron comes in, then that's going to go into the 2pz orbital. Why? Because it's going to get repelled by the two electrons in the 2py and the 2px orbital. And since all the orbitals are exactly at the same energy level, then why bother? So if three electrons are coming into the 2p orbital, then they're going to be filled in this manner, one electron each in each of the orbitals. But what happens if four electrons are coming? Now the fourth electron that's coming in has no option. You already have one electron in this orbital, you have one electron in this orbital, and one electron in the 2pz orbital. So if the fourth electron comes in, you don't have an option. That electron does not have an option. It's going to go into the 2px. So instead of one, they're going to be two electrons in the 2px. If another electron comes in, that's going to go into the 2py orbital. And if another electron still comes in, then that's going to go into the 2pz orbital, and that's how the orbitals are going to be completely filled. But always remember, they're always going to be filled in a single manner first. The fifth point about filling orbitals is that uh, if there are two electrons in an orbital, then they are going to have opposite spins. Now this is a very interesting point. What do we mean by opposite spins? The first thing, let me describe you first, is, let's say I have a 2px orbital. Let's call this as the x-axis, and this over here is the nucleus, positive nucleus, and this over here is the 2px orbital, and there are two electrons in the 2px orbital. Now if there are two electrons, then an electron is going to, since there are two electrons existing in the same region, those two electrons are going to repel each other. So there's going to be repulsion, electron-electron repulsion. So how do two electrons exist in the same region? Now that's a very interesting point. And recall one thing, that whenever you have a moving electron, whenever you have a moving electron, it's always going to have or produce it's always going to produce a magnetic field. And if you recall physics in O levels, you probably are aware of the question. This question came frequently in physics, where you use the right hand rules. You had current I traveling, which basically means that there are electrons traveling in this direction, electrons traveling in this direction. So if you have current I, then the magnetic field that was produced was something like this. And whenever you had electrons moving in wires, then there was a magnetic field, and that magnetic field would attract the two wires. Otherwise, there were electrons in both the wires, so they should be repelling each other. But since the magnetic fields were attracting each other, there was a net attraction of the two wires. The same concept applies to having opposite spins. When you talk about opposite spins, spin on an electron produces magnetic moments or magnetic fields around an electron. So if one electron, let's treat an electron as a particle. So if this is the magnetic moment produced by one electron and it's spinning in a particular direction, and there's another electron which is spinning in the opposite direction, then that electron is going to, and let's say you have south poles and opposite magnetic moments are produced, then those two electrons are going to attract each other. So there's going to be a force of attraction. So the repulsion that is produced when two electrons exist in the same region is basically cancelled out by a magnetic force of attraction, which is the result of having opposite spin. So if one electron is spinning in one direction, the other electron must be spinning in the other direction. The way these two electrons would be represented is there's going to be an upward spin on one electron, and there's going to be a downward spin on the other electron, and this ensures that the magnetic moments produced are completely opposite, and so the two electrons are going to attract each other and they're going to cancel out the force of repulsion due to the negative charges present on both of them. So this is how two electrons would be able to exist in exactly the same region.